Well,
all right.
good. Well, the sad news is that I'm just recovering from a really bad chest infection. So excuse me if if my voice wavers a bit during this talk. The good news is that we'll finish early. So as Eric said, I am going to present on a couple of topics that were due to be discussed at the March face-to-face. Unfortunately, I couldn't attend that meeting because I was called away, but on business. And thank you, Mike Byrne, for stepping in to support Neil for our session, which was on formation damage. But I understand from feedback that it was, as Eric said, it was quite a lively discussion, and we didn't get through all of the material. So this is really just a finish off of materials from that session that was held in March in Bergen. So as you know, the formation damage session in March, it was titled Why, What, Where and When. And I thought that was quite a catchy topic, because it was, why do we do formation damage? Where should we do it? When should we start? And what should we look at? And so the two pieces of information or discussion points that were not discussed in full were these two. It was a well suspension, the risks and implications of well suspension, and then a bit of a discussion around pass-fail criteria. I think both these topics were touched on lightly, from what I understand, but we'll go into a little bit more detail in the next hour. So we did talk about well suspensions a couple of years ago as part of the network, and so these slides are an update on that event that we had. I think it was 2 or 3 years ago we did raise this subject, but this is a sort of an update with some more field and lab data that has come through. So first of all, well suspensions now becoming quite a common occurrence because of several issues, maybe unplanned delays on first oil, maybe FPSOs arriving late, which is a bit of a track record there. Well tiebacks, the cost of well tests. This was one big issue, that the cost for a well test spread footprint on the rig or platform is quite expensive, and therefore to drill a series of wells and leave them shut in until you can flow back, rather than well test every individual well, is becoming more cost efficient. But of course we then need to test the implications and risks of shutting those wells in, and then of course the environmental impact due to well testing. So if we can eliminate successive well testing every well and shut the wells in until we're ready to flow back, then that's more environmentally friendly, pleasing. So well suspensions then, of course, when you drill a well, we will know about formation damage, and we are likely to damage that well in some way. But if you don't clean up or go to injection straight away, is there sort of a damage mechanism that could effectively get worse due to shut-in? And yeah, we sit around and talk about this. Oh yeah, there's a risk of shutting in and damage, but how real is the problem? And I hope this next series of slides will try to put that into context. Excuse me. So with the four primary damage mechanisms, really, when you consider, let's just consider open hole completions. I think cased hole shut-ins are fairly easy to imagine. It's usually perforation damage. but let's consider just open hole completions. And so the risks of damage come from the fluid that's left in the well, particularly if it's solids laden, low solids or conditioned mud. So you get sagging over time and potential plugging of completion, or damage to the formation. The filter cake itself, the effects of time and temperature on the filter cake over time. There's evidence I'll show you later that filter cakes can become rubberized over time and temperature if not flowed back immediately or treated chemically. Precipitation over time, so fluid interaction, the leak off of completion fluid or low solids fluids into the reservoir, mixing with reservoir fluid, formation water or crude. Can lead on, of course, to production issues such as asphaltenes and scale and such like. Also, the fluid rock interaction. And then fluid product behavior is an interesting one. So we have evidence that some materials that are used for drilling fluids and completion fluids can change in behavior. And I guess we're talking here about precipitation or changes in characteristic that can make make it difficult to flow back. Some fluid loss reduces, for example, in oil-based muds, when put under extreme temperature and pressure, can become rubberized, as I say. So yes, so fluid product behavior is something we need to be careful of. Know what's in your filter cake and how it's going to react with time and temperature. And then viscosity of fluids, mobility of fluids that are left in the well over time. So a fluid like a low solids OBM, which looks quite good in lab testing on day one, put it under pressure and temperature, and you may see a different effect over time. And usually it's a thickening of the fluid, which is of concern, of course, with flowback and cleanup. So well productivity risks and associated from these well suspensions, you've got the two elements, the formation damage element and then the completion, the effect of the fluids on the completion itself. And so when I put together this presentation, I've kind of tried to do it three ways. One, looking at industry experience and learnings review. And number two would be to look at fluid design considerations and lab studies. What do we need to do? What do we need to think about and focus on when we're doing the design of the fluids that will be left in the well to minimize damage to both formation and to completion? And then I got some example laboratory studies, some recent examples of that, where we've looked at fluids and formation damage that will be suspended over time. So the first series of slides, then industry experience. Many of you know I'm formerly BP, so a lot of the examples I'll use will be my own personal experience of this type of well suspension work. And so the first real project I started working on several years ago, many years ago now, actually, was for the West of Shetlands, where we were drilling and completing high angle wells, screen only completions. And the hope was that we could condition OBM and run screens in condition OBM. And then these wells were to be shut in for anywhere from 4 weeks to 2 years. Actually, most of the wells were cleaned up relatively quickly before the 2 years. It was but we did look at long-term aging tests. And so here you see a plot of skin versus suspension time for Foinaven, one of the fields in West of Shetlands, and each dot here on the graph is a well. There's another slide coming up where it's annotated with well names and so on, but essentially you can see that actually Foinaven only had really one long-term suspended well, which was over about 18 months, a year and a half. Most of the wells were cleaned up within 5 months, but a bit of a scattering of skin there. And you'll notice there's some negative skins here, which was quite interesting. Well, if you consider mechanical skin, or skin that is actually directly related to formation damage, and say that's, say, measured within sort of near wellbore radius, typically around 0 to +8, 10, something like that, due to damage and plugging. But then you've also got geometry skin, which is more to do with, of course, penetration of the reservoir, KV, KH, well inclination, completion size, and so on. So that leads to global skin of the two together. So initially, you might be recording, when you do a PBU, pressure build-up test, early on in the so you've just drilled the well and you do a PBU, you may be initially measuring mechanical skin, but over time, I'm going to have to move this. Over time, you may find that you're measuring more geometry skin than the mechanical skin. So it's really the skin factors here, because of the shut-ins. We're really talking about global skin, so total of mechanical plus geometry. And if I move on to Schiehallion, these wells were more likely to be shut in. And you can see here again that we've got a bit of a scattering of wells and skin factors, around 5 to 10 for the first 6 months. Not many data points that you'll see over sort of 9 months, which was the point of this slide. And here's the combined suspension time versus skin summary. But you can't really draw any conclusions from this to say that both short-term and relatively long-term, that there really is no trend. And looking at some of the fields in BP, you've got Schiehallion, West of Shetlands. So testing that was done for those standalone screens, we looked at OBM, oil-based mud, ulti-drill actually, static aging of the mud, and then flowing back through screen coupons. So this wasn't formation damage work so much, but just looking at aging of the mud and ability to flow back through screens. And what we found was that we had okay fluids that were going to be used. These were about 1.9 SG, by the way, so they're quite high density. Some of them, early ones anyway, then they went down to about 1.3, but there was a big range of densities that were looked at. And so what we found was that flow through screens was okay up to about 6 months, but after 9 months, we did see some plugging, some agglomeration of solids, and plugging of the screens. And then for the second row here, Schiehallion, West of Shetlands, expandable screens, we did actually do quite a bit of testing of expandable screens pressed up against filter cake, excuse me, filter cake, and then aged, and then try to flow back. And we did find some damage in one of the fluids that was used, and that led to a change out from one mud to another to solve the problem. And that was due to product changing with time, pressure, and temperature. And I've got a slide on that later. Scarve field, drilled and completed, say, 10 years ago now, but really good project that to look at field studies, rather as in addition to lab work that was done, looking at field results, and looking at 1, 2, and 3 month return permeability tests, and looking for any potential damage mechanisms. And interestingly, there we found that we tested a whole variety of different fluids, OBMs actually, all oil-based muds for standalone screen and open our gravel packs. One gravel pack actually was done, a couple of gravel packs, sorry, with aqueous fluid, but the standalone screens were oil-based muds, and we looked at a range of weighting agents from micronized barite to manganese tetroxide, through to API Bayrite. And interestingly, the micronized Bayrite and the Micromax materials did agglomerate over time. And so we actually ended up using an API Bayrite for those wells, which was sort of counterintuitive to us when you're looking at flowing back through screens. And 4 of those wells, I think something like 20 wells in all drilled, if I remember, 17, 18, 20 wells. The first 4 wells were left with OBM in the well. And then we had to change to a low solids completion fluid, screen running fluid, because the FPSO was going to be very, very late. And I've got a slide on that, but I'll come on back to that one in a bit. And then Cyrus, Quad 204 and Kinul, some other examples from BP where we looked at aging of muds and formation damage, and in those 3 examples we didn't see any detrimental effects of aging through core flood or through fluid testing. And going back to the Scarve example, here you see each bar here is a well, and these are chronological order from bottom up to top. And so the first 4 wells here in red, these were vertical wells, gas producers, and were all drilled with oil-based mud and suspended in oil-based mud. But about during this phase of drilling and completion, it was clear that the FPSO was going to be late by up to a year. And so subsequent wells, which were mainly SAS, but a couple of gravel packs, were then completed, suspended with low solids OBM, for fear of damage. We hadn't seen really much evidence in testing we did for these first 4 wells. We said, we're quite happy to leave conditioned OBM in those wells for a while, but over 22 months, as it turned out to be, some of these early wells, 22 months, we thought, just to minimize the risk, we decided to change to the suspension fluid, which was the low solids OBM. And the good results here is that I think majority of those wells, if not all of them, cleaned up pretty well, and were at one point some of the best producers in Aker BP's portfolio. So we were quite pleased with the design work. But the important thing I want to stress is that we did design work. We spent time doing core flooding. We spent time doing fluid flowbacks through ICDs and suspended ICDs and so on, and back and solids back through screens, and all that work led to a successful project. And some of the lab work that was done for that project, here you see we did some core flood work, looking at, initially we were planning to do up to 6 months, but we ended up just doing a 3-month test where we took mud against core, and then we did a flow back. So you can see that this is damage on the y-axis here, and you can see that after 1 month we had a damage return permeability of about 60%. We then what do we do then? We then trimmed the core plug at that point, and then we then did a spin down, which is a typical Corex procedure. And then after 2 months, we did the same thing, but we actually added a bit more data here on minus mud cake and minus the mud cake and minus the screen here, minus the screen and minus mud cake for the last 2 months. And you can see that there's interesting trends. So, the damage is actually with mud cake on getting worse, but when you take that mud cake off and the screen, you can see that there is some improvement over time actually. And this is a trend we've seen recently in other projects, and I'll come back to that in a bit. Other examples here, we got Clarefield. So we did a 3-week shut-in. So these are examples of where we're doing core flood work with muds, flowbacks, and this is acceptable shut-in results after 3 weeks. This example here is a Schiehallion expandable screen test where We looked at one particular we looked at one particular mud. We call it mud A, and we filled we put a filter cake on a core plug. We put the expandable screen in place, and then we shut it in. Now these wells were due to shut in for 2 months, but we only then did a shut in after 2 weeks, and the initial return permeability for the mud on its own with an overnight shut-in was very acceptable, with an 87% retained permeability. But when we shut it in, we got 80% damage, or 21% return perm, and that was repeatable. We then did it again and we put a low solids OBM as a suspension fluid during that 14-day period, and we still got this 20% return perm, or 80% damage number. And we found out that this was due to the filter cake tenacity and its changing properties over time. And so we changed the mud out. We went to a different company and we got much better results. And over a 13-day shut-in, with mud B, the overnight shut-in was very good cleanup at 98% return perm. Then with a 13-day shut-in, we got a 71% damage, and then we did a test again where we put a low solids OBM in there as a suspension fluid, and again we saw an improvement overall. But yeah, basically a non-damaging mud, which we were quite happy with, and the project went ahead with that mud B without any problems. And here you see a picture of the pasty, badly damaged filter cake that really did rubberize over time. And this is the sort of test. Expander was not widely used as much as the standalone screen, but again, you could still get this effect if you're looking at open hole completions, exacerbated by the trapping of the cake with the screen, of course. But yeah, it's important to understand the effects of time temperature on filter cakes. This example here is Quad 204, and this was an interesting one because there were due to be about 25 wells drilled on this project. I'm going back maybe six years now, 7 years ago. And these wells were initially planned to be well tested in sequence. And that would have been quite a lot of time and effort and cost. So we looked at the idea of suspending these wells with fluid. And so we looked at aging over 6 months, core flood work. We didn't have much core, unfortunately, so we did a field core and compared that to a Clashak outcrop core with a short-term turnaround return perm of 4 days. And those results were plotted here on the bottom right graph. So the field core initial damage over 4 days was around 85% return perm. And then you can see the Clashak core was around 70% return perm. So this was our starting point. And then when we continued doing core flood work over 1, 2, 3, and 6 months with just Clashak, we recorded that data, which is this blue line here. And then we were able to extrapolate or guesstimate what the results would be for the field core. Not ideal, but it's all we could do, really. And you can see that there is basically a progressive damage to this return permeability number. But I guess because of previous experience in aging, we the team thought that our projected, look at the bottom left graph here, our projected damage trend was that we would see initial damage, of course, but it would tail off, and at some point there'd be a threshold time at which point it would never really increase anymore, or increase very slowly. Whereas the worst case would be that the damage would continue to extend, which is the red line. So in the top right graph here, you can see that we plotted 4 days, 1 month, 2 month, and 3 month, and we really followed the expected trend. And it was we really followed the expected trend, which was really exciting. But then, unfortunately, our 6-month result kicked that trend, and we had it went off the projected line, unfortunately. But even so, the incremental damage was not that much. So we're talking in terms of going from sort of 80% return perm down to what, 70% return perm. So we're still in success domain here, and so we continue. We basically not necessarily ignored the number. It was an important number, but we were able to make decisions based on this data set of 6-month aging, and so our projected skin profile for that project was, as you see, this dotted line, that skins would be in the region of about 2, just under 2, +2 for the project on suspended wells over time. And this graph here, the green line is our actual Quad 204 data set. The red line is a previous study conducted by Det Norsk, which they did an identical 1 week, 1 month, 2 month, 3 month, 6-month test, and they saw this trend, which is where the trend came from, of some sort of threshold number, which was around here. It was about 3 months where there's no further damage. You can see an indication of damage, of course, within the first couple of weeks, which is something that I always advise. So looking now, then, what did that project do? Well, it saved in the order of $125 million in well testing that was not necessary, and those wells cleaned up pretty much to expectation. Yeah, so yeah, a lot of effort and costs put into damage testing and fluid testing, but golly, was it worth it to save 125 million? That was no way the amount we spent at Corex. Sometimes is, but no, not on this occasion. So next slide then. So some other industry experience, Equinor, they routinely suspend wells for weeks and months. They always leave low solids fluids in the well. They don't really care much for conditioned fluid. And they actually did a review, they actually did a review of 130 wells, and the conclusions were there was no obvious relationship between well suspension and well productivity. For wells with low PI, suspension was not the root cause of the low PI. And they put a lot of effort into fluid stability and mobility rather than formation damage, because they tend to use, I think I'm right in saying that Equinor tend to use a sort of textbook set of fluids, so they think that they know the fluids inside out, and therefore they're more interested in fluid mobility at temperature and pressure rather than formation damage. They focus on low particle content, compatibility with the completion, of course, flow back of solid fluids through screens. They will do tests for up to 8 weeks. Formation damage testing is done, but only for new fields and or new fluids used, and they'll do 1 day versus 28-day testing. Shell, they favour low solids in the wells. They don't have any, well, from last talking to them, they don't have any examples of poor performance due to shut-in. And they don't generally do a lot of shut-ins, as so the feedback I got from Shell. And Total, they do suspend a lot, but actually what they do with their standalone screen completions is that they prefer to use chemical breakers, even for producers, to minimize any risk of long-term damage. So that's their approach to suspension. They'll often put in chemical breakers or fluids that they know will break down easily, smart filter cakes, etc. And finally, on excuse me, industry experience, Vår Energy, some work that was done by MI, and they looked at a 1.4 SG OBM and suspended it in a core with a screen coupon in place for 6 months, and they got a return perm of 91%. So yeah, okay, a lot of data there, but really it's showing you that there's not a lot of evidence to say that long-term suspension, if you use the right fluids, is going to be a big concern. But when you're looking at category number 2, which is the fluid design and the lab testing required, We divide it into 3 areas: fluid loss control over time, fluid stability at downhole condition, and mobility and cleanup, and formation damage of the fluid and rock interaction, which is the core flooding. And I say here, personal experience suggests that most damage occurs within the first 3 months, with an indication of damage within 4 weeks. That's something that we put into recent projects. So fluid stability at downhole condition, consider the importance of fluids left in the hole. So conditioned drilling fluid, low solids, water base, oil base, solids free, gravel pack fluids, of course. The gravel pack wells can be suspended with either viscoelastic surfactants, HEC, biopolymers, etc. And of course, any additional chemicals like chemical breakers that might be in the well. Think about the activity of those fluids on not just formation and screen, but also things like elastomers and tubulars. So it's very important to test if they're going to be in contact for a long time prior to flowback. So fluid loss over time, fluid loss equipment readily available for that. For SAG testing, you've got the Jefferson SAG shoe test, viscometer SAG shoe test, where you can look at SAG index. It's the bottom density over time divided by the combined top and bottom density, which gives you a SAG index for a given fluid. You've got the dynamic high angle tester, which can measure SAG at various temperatures and pressures, and you can angle the cells. You can see on the right hand side various angles to monitor SAG. Back to SCARV, as I said, we did all that testing for SCARV and said, yeah, with sort of 3 to 4 month shut in, those muds can be left in the hole pretty well. And those first 4 wells were indeed, well, these wells in red here on the right hand side, they're all left with OBM 1.3 SG OmniFlow, and they flow back pretty well. But then when we knew about delays, we switched over to low solids, and that worked pretty well. Lab testing. This is for fluid flow back through screens over time. So various labs have various different methods. This one here is an old cell that we put together at BP, actually, which was looking at aging mud in a cell under temperature and pressure, and then flowing back sequentially top, middle, and bottom samples through a screen coupon to make sure that we were getting good flow back through screens over time, and then extracting those top, middle, bottom fluid samples. You could then measure density differences with the different fluids. So we looked at 5 different fluids. This was actually for SCARV. So we looked at OmniFlow with Bayrite, OmniFlow with Micromax, OmniFlow with both, Micromax on its own, and low solids OBM. And we monitored density and gels on top samples, middle samples, and bottom samples. There wasn't actually, much difference apart from there was some plugging due to Micromax. As say, this Micromax fluid and the mixture did tend to agglomerate, and we had doing particle size distribution on the fluids over time. We saw a bimodal particle size distribution rather than a mono curve, if you will. We got sort of a double peak where sagging occurred, so you had 2 peaks of particle size distribution, which we wanted to avoid agglomeration. And this is an example of Wintershall DA from Houghton Bank, and we've seen this one presented by Oliver about a year or so ago, so I won't dwell on this one. But this is looking at methodologies to get accurate rheology tests. You really do need to apply. Conventional aging will not give you a good story about downhole conditions, and what Oliver and his team managed to do was to come up with a procedure to monitor and predict fluid behavior with time and temperature and pressure, which was more important to get accurate. This data is in the previous slide pack, but a lot of testing done on various time factors, various pressures to look at fluid behavior, and those wells again cleaned up pretty well after their shut-ins. Filter cake quality, we talked about that already. Interestingly, with filter cake changes in properties, something that we looked at with BP was the effect of filter cake performance on elevated fracture gradients, more important for injection wells. But certainly you could argue that this also causes damage to the formation, be it unconfined, as in the case of a standalone screen, or confined, as in the case of an open or grower pack or an expandable screen. That your filter cake quality will impact fracture gradient in some way. So again, something to be aware of. And then lastly, this Spirit Energy test program, where we looked where they looked at a series of fluids, 1.9 SG OBM. And for various reasons, they had to look at suspending these wells with mud rather than the ability to go to a low solids, mainly obviously due to the cost of low solids fluids at that density. And so they looked at Barra ECD and then suspending with base oil, or Barra ECD drilling fluid, then going to a clean low solids Barra ECD. They also considered looking at cesium potassium formate fluids. And these tests were done at 1, 2 month, 3 month, and 6 month aging. Really interesting project. So over the 6 month period, these are core flood results, and you can see that baseline 1, 2, 3, and 6 month testing, formation damage pretty high.
Apologies. We have a question from the chat.
Oh yeah.
So from Obina, so they say in these long-term aging tests, do you keep these tests going for the stated number of weeks, months, literally, or is it the aging process accelerated?
No, these are real-time core flood tests and aging tests. So they are not accelerated by any means. They are true month shut-ins.
Okay, thank you. So Obina, would that be sufficient? Okay, she says thanks.
Okay. Yeah, so thank you, Abina. So looking at aging results, we've got low perm core on the left, high medium perm core on the right, but you can see over time there's very little change in the trend lines, which was interesting. And this one here is Barra ECD OBM followed by base oil, screen running fluid, and suspension fluid. And again, only on the high perm core on the right do we see a buck in trends here. As you go from sort of 3 to 6 months, you're getting a reduction in damage, which is interesting with the base oil testing. But yeah, so again, a whole series of tests done because of the importance to shut these wells in at 1.9 SG. And worrying about the risks of such shut-ins, but we saw that there was no trend whether they cleaned up on day 1 or left it for 6 months. Then you got the filter cake. You're able to look at filter cake thickness over those tests as well. So here you see Barra ECD and then the Barra ECD base oil combination, and looking at cake thickness over time. Previous work by this crew in 2021, they were seeing filter cakes around 18 millimeters. Excuse me. they were seeing they were seeing really thick filter cakes, obviously muds that had not been properly prepared or designed properly, but with effort in product usage, concentrations, so on, they were able to reduce the thickness of those filter cakes way down to single figures, which is excellent news. So again, something that can be done, filter cake quality over time with reservoir condition equipment. And then looking at fluid mobility over the 6-month period. So looking at the sag factors of top, middle, bottom density of fluids over time. Now, I'm going to move on to case studies, and I think Arna's on the call here because I just wanted to talk about this briefly. I think there was a big debate about this Yggdrasil, formerly called NOACA project, at the March meeting, and the amount of lab testing that was done. But I just wanted to reiterate the importance of this testing, because there was a need to, because of the incumbent fluid provider on the project and some forthcoming tenders, it was really important because of the variety of wells that were going to be drilled, that will be drilled, at the various pressures, temperatures, completion types, you name it. It was a really complicated project, and so really to get a good idea and handle on the best fluids for the project, it was deemed necessary to do an extensive program. And so I was working alongside Arna, and we looked at the 4 fluid vendors that were providing fluids for the project, and there were 4 various completion types that were needed for the project: cased and perforated, standalone screen, cased and perforated water injectors, and standalone screen water injectors. And then various scenarios were going to be tested: the base drilling fluid, the drilling fluid and completion fluid, and then the suspension, because these wells were going to be shut in. Some of these wells will be shut in for up to 15 months. So again, fears about risks of that. We could go on past history and say, well, we don't need to worry about this, but not a good philosophy really, or approach to a high profile project such as this. And so this slide really gives you an idea of the variety of well fields, temperatures, pressures, mud densities required, completion types, and a lot of the characteristics of the wells were outside common experience. So these wells, for example, here are on Frigg, Gamma Delta, and Fuller. We're going to be shut in for over 15 months, and we don't have a lot of data on that. And then you've got high density fluids here used on Fuller and Little Frigg, and you've got high density 1.9 to 2 SG, 1.4 to 1.6 SG. So, again, not a lot of field experience or lab experience in testing these fluids, and so on. So this was really the driver for the number of tests that were required for that project, and it's been very successful. The data's still being analysed actually, but the first thing that we did was to look at the risk factors of what are the damage mechanisms that could be caused by shut-ins, and we did this for both oil base and water base. And here you see the oil base chart, where we're looking at the risks associated with filtrate invasion, which would be mineralogy, emulsions, rel perm impairment, saturation change, etc. Pore throat plugging, hull mud losses, screen plugging, brine invasion, and so on. So you do a risk assessment and the likelihood of damage, and then you comment. And then by doing this, you can then focus on the tests that are important, looking at formation damage, impairment, and behavior with time, looking at wellbore fluids, behavior over time, and so on. And then with each of the fields and the different completion types and the different mud densities, we looked at analog field studies. So, for example, with the Frigg Gamma wells that are due to be drilled, which is a open oil producer standalone screen, a mud density of 1.25. we could look for analogous field studies and lab studies. So Scarve, Schiehallion and Foynaven, we talked about those. And then you've got the high density Fuller wells and Fogelberg, which would be a project that is in the public domain, testing that's been for Fogelberg, that was relevant for this Fuller. And then you've got Lillfrig, Gerlpack, gas producer, standalone screen, and oil producer, cased and perforated. So again, some examples: Fogelberg, Chardonnays from BP, and so on. So we're able to look at offset and analogous wells and what their approach to fluid design was. And again, looking at Yggdrasil, plotting some of the results that have been coming out of the work that Anna's been doing. This is just a snapshot of some of the data, but you can see here that looking at 6-month shut-ins, here you can see mud, this particular mud that was used, and you're getting a rel perm on day one, T0 of 100% return permeability, but over even up to 3 months, we're getting a decline just with mud alone. But then you take that mud one and you add a low solids OBM completion suspension fluid, you're getting a similar trend, but it's less damaging over time. But then when you change the low solids to base oil, you're getting an improvement. So you're getting an initial dip over 3 months, and then you find that you're getting a restoration of permeability, or it basically is cleaning up over that period. And then we changed and looked at a different mud with the low solids, which was this orange line, and we got a similar trend, but not as good. So yeah, so we're getting some interesting results on that data, which is, as I say, still being tested. We on the whole, we've seen some really good results on the fields, really good regain injectivity and for the injection wells, and some return permeability numbers. For each of the fields, we targeted a flow rate which would actually a flow rate in the field which could be upscaled to a lab rate that could be upscaled to field rates. Is what I'm trying to say. So for each of the different fields, our flow rates change. So, for example, for Frigg Gamma Delta, a 1 milliminute flow rate was adequate to test formation damage. But you go to the Fries and the Fullers fields, and you're looking at much higher flow rates required to equal field projected field rates. We've got a problem with one of the fields, that field, which we're still working on fluid formulations on that. But essentially, an important project, high profile, and I say putting a lot of effort into fluid design. And lastly here, excuse me, this is a Corex project that was published where they looked at case studies, shut-ins over core floods, 24-hour, 4-week, 8-week, 13-week, and 26-week shut-ins. And then case study 2 was looking at a combination of water-based tests and an oil-based test, up to 3-month shut-ins. And this is basically the plot from that study, which shows again not much change with core floods over that period with the various fluids. I won't dwell on this because I think I'm labouring the point. I got one slide on a recent study.
Alan, apologies again. We have another question from the chat. So
okay,
I don't know if you see that or.
Okay.
Should I read it?
Oh yeah, I can't see on my screen. I'm sorry.
Okay, yeah.
Sorry.
So yeah, no, sorry. Is the risk for formation damage, increased skin upon well suspension fundamentally different from injectors and producers?
Oh, that's a good question. I think it is different because with injection wells, commonly chemical breakers are used, which are not common in producers if used at all. Some operators, like I said earlier, Total tend to use breakers for some producers, but generally speaking, for injection wells, you really, it's unusual to drill an injection well and then leave it shut in for a long period, whereas oil producers tend to be more likely to be shut in for longer periods. So yes, there is a difference really in the approach and the program from producers to injectors.
Okay, thank you.
Because with an injection well, you will actually design the fluids to be easily cleaned up to allow injection. Either a flowback will occur and then shut in, or you'll put a chemical breaker in. So it's a different approach, and I'm really focusing here on producers, yeah. But that's a good question. There is a slight difference in approach, yeah. So for Pecan Energies, this is a project off Ghana. Again, a really high-profile project, and a whole series of wells to be drilled, standalone screen and gravel packing. And so we did a assessment of basically 8 phases of testing, where we looked at OBS, basic oil-based mud, oh, excuse me, and then looked at oil-based mud for injection wells, because these formations are quite difficult mineralogy wise, and a lot of shale. So it was sort of it was preferred to use an oil-based mud for producers and injectors. So we looked at an oil-based mud drilling fluid and an oil-based breaker for injectors, but we did also look at water-based mud for injectors and a breaker in case the oil-based systems didn't work. We looked at completion fluid, which is phase 3. We looked at water-based injection fluids, phase 4. We looked at low perm core for water injectors. We did an assessment of the gravel pack fluids on their own because they were quite a new technology, and then we looked at stack up, full sequence core flooding, short term, and then we looked at long-term suspension. We got passes on all tests up to the phase 8, which was the suspension time, and we've seen some fails, and these fails are possibly coming from the gravel packing fluid, we're thinking, and so that's more work required. But we had some issues with phase 6 gravel pack, pumping gravel pack fluid, or simulating losing gravel pack fluid into formation, and we had some pretty high damage from these sort of xanthan-based systems. But we managed to cure that. So we had the companies reformulate the fluids, and we got passes on that. But when we did the full stack up, we come up with a technical hitch there, and we're getting some failures. So it's work in progress. But again, importance of formation damage studies for long-term shut-in wells. So the conclusion then of that, there's no evidence that wells will be damaged beyond repair if suitable lab work is carried out. RDF and suspension fluid design is critical to make sure that we get no damage, and or sagging, etc. in fluids, and evaluate the impact on formation and completion. So both, not just formation, but also look at screens and the ability of fluids to flow back through completion. From lab work, an indication of incremental damage can be seen within 1 month. I stand by that. Optimize fluids at this early stage of work, and then do a 3-month check. Once you've got your 1 week to 1 month testing sorted out, then just do a long-term test as a double check. Fluid stability and mobility is important in aging tests, and if at all possible, of course, suspend the wells with low solids-free systems. And that's it really for that section, and feedback from you guys on your experiences that I haven't covered or I don't know about would be really useful and handy. So perhaps we can open up a page on the portal where we can maybe continue to share experiences with well suspensions or lab work that's done for these projects. That would be very, very useful. I'm just looking at the time. It's 10 o'clock. I've just got a couple of slides.
Yeah.
Won't take too much.
Alan, we have a couple of more questions. Maybe this would be a good time to
Okay.
take those.
Yes.
So we have one question is the formation damage permanent, or does it disappear over time as you flow back the wells? Is this ever tested in the lab?
That's a really good question. So what we're measuring in return permeability is an initial damage. It is expected that over time, for example, that damage should reduce in time. But of course, with lab testing, to do prolonged flowbacks can be quite costly and time consuming, of course. So yeah, this is an initial well on production. This is your initial damage snapshot. So this is a debate which I've had quite a bit with Cinnamine, actually, where they talk about the fact that formates, for example, tend to, in lab testing, often will be disappointing results, but their view is that it cleans up over time, and they've proven that. So I think to answer that question, yes, there is an expectation that initial damage should improve with time as the well cleans up over time, but it's very rarely tested. But of course, it's important if we can design the fluid to flow back or clean up with good numbers from day one or T0. That's what we strive for, to avoid a high skin initially. So I hope that answers your question. Yeah, there is an expectation that it should clean up to some degree, but it's often unknown to what degree.
Okay, thank you. And then we also have another one. The recovery in return permeability at some point in the aging process. How would you explain this phenomenon? I.e., what is the physics leading to this recovery?
Oh, okay, let me go back. This one here, I guess. Yeah, so let's take, so this is a trend that I saw previously on an earlier slide. I think I was talking about Scarve, where we saw initial decrease and then a recovery. Yeah, it's case specific. It could be due to these are all return perm after aging with a filter cake in place, and so with the mud you can understand that this is obviously a mud which the filter cake clearly is hardening with time, and then you've got this trend here, which is the basal one, which we quite like, where you're getting a damage that's following the mud trend, but then you're getting this increase over this 3 to 6 month. Now, that has been repeated here to a lesser degree with the low solids OBM. So my interpretation of that in this example would be that the completion fluid that's in contact with the filter cake is somehow fluidizing it over time. So you've got an initial downward trend, but then something's loosening that cake here, be it base oil with the grey line or low solids OBM with the orange line, and that's that example. In an earlier one, we saw a recovery where we did a trim, and so the cleanup was actually internal in the core, and that could be due to other phenomenon, like you could have. I know that Mike's done some CFD work on this, where you get over time you get fluid banking, and fluid movement within the core, or on a larger scale within the reservoir. So you could get, for example, formate fluids, which on day one of return perm testing may show you a high damage. Over time, that formate fluid could actually, through gravity or whatever, dissipate deeper into the reservoir. So you get a cleanup effect that you don't see on day one. So I guess there's no one explanation for it. It really depends on each case individually, the rock type, the fluid type, the chemistry, the mineralogy. That's all I can say. And that can be tested and diagnosed from these tests, I guess, is what I'm saying.
Okay, thank you.
Is that it, Eric?
Yeah, I think
Yeah,
I would,
okay.
would
Good.
pass, but we'll see if in the chat if that would be sufficient.
Okay. Yeah, good. Thanks. Yeah, sorry, I can't see the text on my screen.
Yeah, no worries. I'll read it out and let you know when they come in.
Yeah. So I just got a couple of slides here on testing pass-fail criteria. And so typical work program for fluid optimization is everything from fluid drillability, which is most important. So, looking at mud weights, viscosity, and muds that will minimize hole problems. So it's a drillability issue. Then you're looking at shale stability, so shale mineralogy, XRD, CC. Sand characterization, everything to do with the sand size, pore throat size, permeability, porosity. Fluid compatibilities, mixing drilling completion fluids with formation fluids. You got your formation damage screening, which is your core flooding, and I will add their completion damage screening, mud through screens, etc. Then your return perm testing or retained injectivity, and then filter cake properties, as we've covered, and cleanability. So a whole range of tests, and so for every new project, this network will understand the importance of coming up with a list of minimum test requirements for a given reservoir section, is what I'll say. And so for fluids optimization, I always think that looking at the shale is as important as the sand, for hole stability reasons and for ensuring a non-damaged screen and so on, and or gravel pack to make sure if gravel pack efficiency is 100%. So core selection critical for sand and for shale. Look at average permeability. Can we just use average permeability for the testing, or do we want to go one step further and look at low, medium, and high permeabilities? Evaluate shale reactivity, as I said earlier, that's as important as sand testing. And so looking at minimum test requirements and pass-fail criteria for each of those tests. I'm not going to go too much into detail on everything, apart from I wanted to focus on formation damage core floods. And some time ago in BP, we looked at the comparison of lab formation damage data versus actual field data. And so what we looked at was try to put some science, if you will, behind return permeability numbers, because we were generating a lot of data, a lot of return perm numbers. What do the numbers actually mean in terms of skin or productivity? And we tried to benchmark that for both producers and injectors. And so some of this is a guide that we put into a workbook that was being used at the time, where we would look at pass-fail criteria for return perm for case perforated, open hole oil producers, gas producers, and water injectors. And these were sort of guidelines. They weren't fixed rule. We could make some allowance for different fields, but we wanted a starting point. So for cased and perforated, for low perm rock, we said a return perm of about 50% or above was really what we were targeting. And as we know, higher perm core is more forgiving for damage. And so as we looked at high perm core, then our targets for return perm we were allowed to reduce those. For oil producers, open hole, we looked at around, a target of about 70% return perm for low perm core. But look at the high perm core. We were able to accept quite high damage, 70% up to 70% damage on the oil producers. And we found for gas, looking at a lot of gas return perm work, we generally found that gas return perm numbers were generally poorer than equivalent oil producer tests, if you know what I mean. It seems to be that the gas was not as efficient in the lab as oil as cleaning up core, and so we allowed for a lower return perm number on those gas producers. And then for water injectors, we used to use about 25% retained injectivity as our target, because all we were trying to do there is make sure that we were getting some permeability in our filter cake, be it through a flowback and then injection, or be chemical stimulation of that filter cake, and get initially some injectivity. And what we generally found was that our initial injection was high, around, I don't know, let's pick a number, 70, 80%, but then it would degrade with time. But as the filter cake reformed, or particles reformed a filter cake back on the sand face. So as long as our end number was in excess of 25%, we were quite happy with that, because it meant we were getting some water into the formation, which was cool the formation and lead to a reduced fracture gradient. That was our theory and philosophy. But yeah, higher the better, really. But if we can get 25%, we were quite happy with that number, and we use that for many projects. And here's a slide taken from Aker BP's manual on when to do a formation damage study. And they've got this really good checklist. If you basically tick yes to any of these questions, then you really should be thinking about formation damage testing. Is it a new field development with no previous history? Is it a field where significant skin or formation damage has been attributed previously to fluids? Is the fluid to be used first a use for a particular field and operator? And so on. And I think this is a really good checklist, really, for determining whether or not to do tests. And some of the guidelines that Aker BP, for example, are using. This is an example of their acceptance criteria for producers and injectors, which is not far off where I was talking about the earlier BP ones. The BP one more recently may have changed. I'm not sure, but I was basically reporting my experience there. So acceptance criteria then for producers, they're looking hopefully around 60%, over 60% return perm. But as it says there, in some cases, lower values can be accepted. And I think that's a very valid comment. It's a case-by-case basis. Sometimes you won't be able to achieve what you need after many tests, and therefore then you look at what's then the impact on skin damage, and can you live with that skin and reduce productivity, for example. Excuse me. And this is I took this from Neil Fleming's presentation, where he's looking at high focus on fluid mobility and focus on PSD to minimize damage, but not necessarily doing any core flood work. Equinor tend to in most recent times, and it's not a criticism or a comment, it's really just a statement that they now have very strict rules on when to core flood. And it's interesting, they deem this page here when not to test rather than when to test. And so they say not to test for standard drilling fluids. Well, okay, that's fair enough. But I think if you use standard drilling fluid in a new field, then I think you'll be looking at doing core flooding. If the permeability is over 1.5 Darcy, very forgiving for damage. I tend to agree with that, but focus on PSD. Chemical breakers, they're using discs rather than core flooding. Again, I think that's a very valid point. And then injection wells, not required to do core flood work, because I guess their philosophy is that a lot of these matrix injection wells are not sustainable, and you'll at some point be ended up fracturing those rocks. I tend to say that if you can maximize matrix injection, and sometimes that's really what you want because you cannot go above cap rock fracture gradient, then I think you would be looking at doing core flood work for injection wells. Certainly disc work and use of breakers there. So conclusion, there's no industry standard on pass-fail criteria. Every operator, I think, would have a different approach, and that would be because of the field conditions and the history. Some evidence that current industry trend is to reduce the amount of test work done, and this is really down to trying to reduce costs. I think it's clear there's a reduced capability in the service companies. A lot of, I'm not naming names, but I know a couple of the mud companies have reduced capability in terms of core flood work and technology development and research. Their labs are shrinking, and I think with standardized fluid systems, there is a sort of common thought that, well, we've used this mud A before and it's okay. Is this the right approach? And with that, I'll finish my presentation. Thank you for listening. I'm sorry about the coughs. I struggled through.
Yeah, no worries. It went really well. Many thanks, Alan. That was a great talk and very interesting. So I think we now can open up for other questions and also if people have other views or things they would like to discuss related to this topic.
Yeah, maybe I can just comment. So thanks, Alan. That was really good. A lot of new stuff in there that I hadn't seen before, particularly on the well suspension. But on the pass-fail criteria, as some of you will probably know, I completely disagree with pass-fail criteria based on core flood tests. If you don't take into account the depth of the damage and the length of the well, then those numbers are kind of meaningless to me. Obviously, I have a particular approach that we've been using, which is to upscale using numerical modeling. But the depth and well length are critical because you basically get different answers.
No, I would agree with that. I think I'm becoming more aware and a supporter of your numerical analysis, but I think in absence of that, and not all projects have the luxury of being able to do that yet. I think to have some indication of near wellbore damage is still valid. It may not be able to pin that number down, so the pass-fail criteria becomes meaningless, as you say, if you're not taking into account full scale, full field, approach to the subject. Then yeah, but I think it's still valid as a test, as a look-see. But don't get too much hung up on pass-fail criteria. I think that's the reason why we all struggle to come up with what is the right number.
No, absolutely, and I think the danger is, and it's in the front of all the CoreX reports. I think because operators have asked for it, but they sort of will have a cutoff of say 30%. And you know, if you get more than 30% damage, it's red, which kind of, you know, is red for danger. But you know, you could have 31% damage would be red, whereas 29% damage would be amber. And to me, you know, that's the danger in these pass-fail criteria, because it's not that simple.
Yeah, yeah, I agree with that. Yeah, I guess thinking about it again, I'd be interested to know if you've example. You don't have to share now, but be interesting to know if you have examples whereby, you know, lab testing has shown a failure, but CFD modeling or American modeling has shown, well, actually, it should be okay.
No, absolutely, and there are lots of examples. One thing that springs to mind is we were recently doing some work where we're doing full well modeling, but the operator wanted us to include a skin of +10, a formation damage skin of +10, and you would be astonished how much damage you need in the near wellbore to get a skin of +10. So how much reduction, you know, how much mud cake, how low the mud cake permeability and the invaded zone permeability have to be, to the extent that I doubt if there are many wells ever that have formation damage skin of +10, and yet it's, you know, +10 is not considered that bad for some completions and some well types. But it's an incredible amount of damage when you start looking at what it would mean in terms of a core flood. Basically, that's kind of doing it the opposite way, but it illustrates the same point.
Yeah,
Indeed.
Skin sometimes, well, maybe I say it's not an absolute value, but I try to say what I mean there. Skin of +10 are in a permeability of, say, 0.5, just choosing a number, 0.5 millidalcy or 1 millidalcy, is quite different effect from that same skin of a 10 in a 50 millidalcy or 100 millidalcy reservoir, isn't it?
Well, the skin is still the same, but the permeability reduction will be quite different.
Yeah.
Yes.
Yeah.
As an impact, okay, call it, yes, the impact, if you say permeability reduction, we're saying in near wellbore area, which is what the skin is, you know, how much extra delta P you have in the near wellbore area. So looking at that number, okay, say my reservoir permeability is 1 or is, you know, 50 millidalcy. If I put a skin damage of 10, it's not, but it's a number 10, the impacts are different. Okay, that's one thing I have. The other thing is in the CFD modeling. Okay, I think having seen some of the things, okay, you've shown it, described in the past. Okay, I think it's a good front, but also to realize, to say that the values you need to put in there, i.e., the mod fluid properties. Okay, is this always explicitly described, or you need some of these lab test results to go in there now to tell you what that will mean in terms of how far they're going to go in the reservoir?
Yeah, no, and I think the lab testing is still very important, and it can provide that input into the full well modeling. So absolutely, you need those tests to tell you what the mud cake permeability, what the filtrate zone is, and what the depth of damage is. So that they are, you know, you can use typical values, but actually measured values are much more valid. The kind of measurements that Alan's been talking about today.
Okay. All right, fair enough. So the idea is, you know, just having that cutoff, you know, is something we'll be careful with, but getting the actual results and putting them, extending them with the numerical modeling will help a little bit more. And that's the conclusion we'll take. Is that?
Well,
Well, line of reasoning. Sorry.
That's my conclusion, but it's not necessarily everybody's.
Okay, fair enough. Lines of reasoning, I think it will maybe a better way to perhaps a better way to put it. Yeah.
Yeah.
Okay. All right. Thank you.
Any other questions for Alan?
Okay.
Yeah, I think
Good.
we're getting there.
We're
now.
done. We're done. Yeah, just a thought, Derek. I don't know if you. I'm sorry, I missed the beginning of the session. I do apologize again for that. Did you mention the next session? Did we choose a date for the next one?
No, we haven't chosen
Okay.
next date for the next teleconference. We have agreed we should aim for a teleconference in September.
Okay.
So that is the plan now for the next teleconference. We don't have a topic for that yet, but that will be sent out as soon as we know a bit more about that. Also, we can mention that we have had a committee meeting for the network, and we have agreed on the membership fee for the companies. So these the invoice for this will be sent out to the contact persons for all the member companies shortly.
So, Eric, just want to mention as well, for in case people aren't aware, we would probably normally have another session in August, but we're not having one in August because we have the European Well Performance Forum in August in Stavanger, and that the dates for that are the 19th to the 21st of August. It's not part of the network, but it's closely related to the network. So we didn't want to have a network session in August, but we're aiming for September for the next quarterly meeting.
Yes. Very good. Okay. Well, if there are no more questions for Alan on this topic, we will conclude. This session will, as mentioned, be it is video recorded, so it will be uploaded. And to your point, Alan, we will then open up for a Q&A for this session as well, that people can continue with other questions or comments they might have for this session.
Okay, very good, thanks.
All right, but thank you very much.
Thank you.
We conclude and we stop the teleconference.
Thank you. Thanks, Eric.
Okay, thank you.
Thanks, everyone. Bye.
Okay. Bye.